got to the point where we could actually take pictures of a Kuiper Belt object. So, just in case some of you weren't here yesterday, I'm going to just remind you, we were awarded this mission as a Pluto Kuiper Belt mission. And that was the goal right from the start. So, we launched from Earth, we went past Jupiter. Jupiter, we did a little bit of science, but that was just, a kick in the pants to get out there. And we got the maximum boost from Jupiter if we went and did the flyby in 2015 when Pluto was passing through the great plane of the solar system. And then also, that meant that we went through and were able to actually explore the Kuiper Belt afterwards. So it's always the goal all along to try and go to the Kuiper Belt, even though it took a little bit of a while before we actually found one. The spacecraft, it's a small spacecraft, it's light, it's lighter than that now because we burned a lot of fuel. It's got even less power than that because the plutonium is slowly running out. This is a chunk of plutonium up here. Basically, our RTG is plutonium plus a thermocouple. It's the simplest possible power source you can have purposely because you don't want it to break. Most spacecraft have reaction wheels to move them around. Now the reaction wheels break, so we just have thrusters, and so those are little thrusters on there. The only moving part of the entire spacecraft is the valves for the thrusters. And here's our science package, and you can see we've packed quite a few instruments in here. We have Lori, our camera, Ralph, our sort of camera spectrometer. Both Lori and Ralph actually have British-built CCDs in them, made by E2V, and if you go to the Science Museum, you can see the flight spare for the Ralph CCD, which is really cool. We have Alice, which is a UV spectrometer. Alice is one of a series of these things. There was a Rosetta Alice. There's a Alice that's orbiting the moon right now. So it's a very well characterized instrument. It's been all sorts of things. Rex is radio science. That's a collaboration with the Germans. Salt and Pepsi are solar weather instruments, basically. At the moment, we're the only thing actually measuring the solar wind far from the sun, but in the plane of the solar system, because the Voyager probes are very much outside the plane. And then finally, we've got Dust Counter, which is down the bottom. Now, Dust Counter is actually built by undergrad students at the University of Colorado. So, we launched, very quickly went past Jupiter. Very quickly went past Pluto, took the big pictures. And we got out into the cold classical belt. And so this is the real intention of the extended mission is to go out into the cold classical Kuiper Belt. The Kuiper Belt has a lot of different parts to it, but the three major parts are the cold classicals that are on these nice circular, low eccentricity, low inclination orbits. There are the resonant objects like Pluto. They're in orbital resonances with Neptune. That means that they formed much closer to the sun and they got dragged outwards by Neptune when Neptune came out. And then this sort of messy stuff out here, those are the scattered disk objects. And scattered disk objects are on all sorts of crazy orbits, and when a scattered disk object comes close to the sun, then we call it a comet. And these are all basically genetically, they're the same thing, but they've had different things happen to them. So scattered disk objects are scattered out, the resonant objects, attracting resonances, they've had stuff happen to them. But the cold classicals haven't had anything happen to them at all. They're the most untouched thing you can go to in the solar system. That's why we wanted to go. We barely knew that this population existed back in 2001 when the mission was first approved. And the case that basically nothing's happened to them has only increased since. And I'll just note that, you see, they're all over the sky. And Kathy was just talking about the dark energy camera. I love the dark energy, but it's actually a really good Kuiper Belt object finder. I use that quite a lot. So, talked about yesterday, we did these stellar occultations, and we got this shape that sort of fit two circles. And so we said, okay, it could be sort of two objects that are kind of next to each other, or we could have got two objects that are orbiting around each other. We just happened to get them when they're lined up. It's unlikely, but it's possible. Or we just had sort of one lumpy potato that had a bite taken out of it there. Didn't quite know. But that's the state of our knowledge pretty much before we got there. So we built up a timeline. Now, New Horizons, it's about 6 light hours from Earth. So we don't actively control it. We pre-program sequences and we upload a sequence, and then it runs the sequence. And so it's, you know, like programming a VCR used to be. You have to plug in everything and then step away and then hope it all works. So we built up our sequence and we started taking data in August. Because that was the first point where we could possibly detect it. And then we were taking data all the way in through December. We did the flyby on January 1st. We didn't plan it on January 1st. We kind of didn't want it on January 1st because doing something like that on a holiday is always annoying, but orbital mechanics doesn't care about holidays. That's when it was. And then immediately afterwards, we went to solar conjunction for a few days. So basically, the spacecraft was behind the sun. Now, that's really a problem for if you're very close to the sun. So it was saying for Hayabusa that they're behind the sun for a while because the angular size of the sun is pretty big. Angular size of the sun relative to New Horizons is pretty small. So it was just a few days where we were knocked out. And then we're in this section here where we're taking down a whole bunch of data. And there's no little yellow section there. We'll look at some other KUs along the way. So this is when we first detected the object. Now, you can't see it in there. That's not it. That's a star. It's sort of like the little wart that's on the side of that star. So in order to do this, we had to take a whole lot of images. This is like a stack of 96 images that we brought down. And we had previously taken another stack of 96 images before it showed up, before it was bright enough. And you co-add them all together, and then you take this subtraction, and what you're left with is that little residual there, a little positive residual, and that's M69. So that was our first detection. Basically, beyond the pixel it should have been, so that was good. And then when you get a little bit closer, it becomes a bit more obvious. But even there, you can barely see it in the coad, and it's much more obvious. We can do the subtraction. So we did a lot of those images going in, looking for moons and for rings around M69. And controversial this one because this is one that I made and it looks a bit funny, but this is taking a lot of different images as we were coming in. This is about 300 different images taken at least 20 different times. And you co-add them and you add them at the same physical scale. So we had two different options for flying past M69. If it looked like there's going to be a lot of hazards, we could go out to our alternate trajectory that would have been around there in that ring and said 10,000 kilometers. But where we really wanted to go was our prime trajectory, which was 3,500 kilometers. And that's where the X is, right there. And it's 3,500 kilometers because when we did sort of negotiating the distances, the imagers wanted to be at 4,000 kilometers, so the images weren't quite as smeared when they get in. And the spectroscopists wanted to be as close as they could, so they said 3,000 kilometers. And we split the difference and said 3,500 kilometers. So we did this, and if we had any satellites around here, it would have just been a static blob. This is a bright star, and it's sort of going this direction here because the angular scale is decreasing as you get closer and closer in. We saw no bright spots there. We saw no rings going around. The system looked really clean, which the engineers loved because if there wasn't a risk, but it was also been annoying. can see that's 3,500 kilometers, so we're not really sensitive to the inner few hundred kilometers. So if it was a tight minor, you couldn't see it that far out. This is the first time that we were able to actually detect it with our highest resolution mode. And it's just like a dot there. But the angular scale of that dot means that it was really hard at that point to say that there is going to be a binary. So we kind of knew a few days out, it's probably not a binary. That's about all that we could tell. There's some annoying residuals, so it kept popping up. And then right before the flyby, we downlinked two what we call fail-safe images. And these were, just in case something broke. During the flyby. We got down fail-safe A, and it was clearly elongated. So hey, we got shape for the first time. And so that's the original image. We got down a few of them, and then we had some very clever techniques for taking these sort of very blurred images and reconstructing the shape they should be. And that was sort of the reconstructed shape we got out of it. And it's kind of sort of like a pizza slice that's had a little light taken out of it. That was kind of cool. And then about a day later, we got the fail-safe B. And this is a bowling pin. So this is the first indication from the spacecraft, not from the occultations, that we actually had our contact mirror, that we had two separate lobes of objects. So you got a small lobe there and a big one over here. And that was the best image we had down before the flyby. If the spacecraft had just decided to not take any images after that, or to stop working during the flyby, that's the best we would have had. But even at that resolution, we were able to tell that it was rotating. We were able to tell sort of its rotation rate from there. And then we were seeing it basically pull one. Just because of the way that you're seeing basically the same area as it moved around. So that's what we had before flyby. We had the spacecraft after the flyby had a phone home, and we celebrated, and got all the kids to go in the front. And that picture got on the front of the New York Times, so a bunch of kids got kids to claim for the rest of their lives. They went on the front page of the New York Times. But after all this, we went over to the geology room and eagerly, looking for the first images to come down, first downlink. And this is the first downlink that really got us excited. And you can see, so that's Photoshop giving a photo on there. We were really excited by this, which is, it's kind of flipped around, and you can kind of see it on the projector. Can you see that this area is a little bit brighter? So, this is a CTD, so it reads out line by line, but you also get vertical banding on it when you have a bright image. And we remove that afterwards with a step of processing. But before we do the processing, you get that vertical banding. So what that meant is, there's vertical banding there. The only thing that would be bright enough to cause that is the object. So as soon as we got that first view, we knew that it was on the very first frame, which was a huge risk. We didn't know it. We had a big long strip of images. Maybe it was going to be one of them. The very first one, space on there, and sure enough, there it is. And you can see some stars in the background. And if you fix the stretch on it, there it was. So right in the very first image, we have it. And a full year of investigations between that and that. But so this is the first two images that we got down, the CEO1 and then right afterwards the CEO4. And Brian's got some great techniques with is fancy glasses. But if you don't have fancy glasses, the quickest way to show this stuff is just with a quick back and forth. And your brain can interpolate very well between those two. So those are the first two images we got down, and right away you could see shape. In fact, you can see that this one is kind of flat. It's actually kind of obvious even in this GIF. So remember that. So we were all staring at it. Unfortunately, I showed up in all these press release images not wearing my shirt because right before we got up the down week, I spilled coffee on my shirt and I went to change it. And I thought, oh no, it's not going to be any more pictures. And then this picture shows up. But there's Todd Lauer, who is our image wizard, and Ted Stripe, who's another one of the image wizards. Ted's actually an amateur. He's a philosophy professor in Tennessee. He really likes doing this stuff. Todd's a galactic astronomer. But again, he's really good at doing the image processing. Between the two of them, they did some great stuff. There's John Spencer, again, really great at doing this image stuff, and who has basically done a lot of the planning for this. And Andy Chapin. So if you've read Andy Chapin's books about space history, he's a really great guy and was writing a lot of our press releases. So we had this sort of running tally on the board of what the shape was going to be. Like, it's kind of a lima bean shape, and then it sort of gets a bit more regular, and then a bit of a neck, and then, hey, we got a nicely defined shape there. And I think this picture is baffled dolphins. So here's Joel Parker, who is, he's on both the New Horizons and he was on the Rosetta team. And because he was on the Rosetta team, he knew a lot about Comet 67P. That's his best way to say it. And had modeled here, so he could describe some of the shapes that we've got with 67P, and those very much on our mind through the flyby. Now the scales are different by about a factor of 10. CG is much, much smaller, but these things are fairly common. And then here's Mallory. And Mallory is an undergrad at North Carolina State, but she's an excellent sculptor. And so, the moment we got these pictures, she pulled out the clay and started making a model. And if you saw a model of the press conferences that she had made that. So right away, as soon as we had it, she had her carving that out and was making models. And here's Mark Bowie. So Mark was the organizer for all of the occultations. He's holding a model there that was made from the occultation shape up to the real thing. And you can tell from the grin on his face how pleased he was. So we had that, and we had over the geology room. We were really excited about we had these monochrome images. Lori is an unfiltered imager, but we also have the color imager, which is about a quarter of the resolution spatially, but it actually can see colors, and then it's actually an imaging spectrometer, so we'll be able to get spectra all across the surface of the object. But on first pass, it was pretty much uniform in color, which looks kind of boring, but it tells you a lot. Because if there were two different colors, that would imply that, they formed in two separate places within the disk, and they came together, because there is a diversity of colors of these objects. But the fact that they are pretty much identical color tells you that they formed together, and they've been together since the start. And that color itself, so the co-classicals are the red points here, and there's a variety right across, but it's right in the middle of it. And you can see the other pectoral objects. There's a big spread of their colors going across, but the co-classicals are pretty much all grouped together there, and it's right in the middle. So we got a nice typical object. And it kind of gives you an idea for how hard the encounter was. That basically we weren't trying to target another object like Pluto. We were trying to target basically something the size of a crater on Pluto. And nailed it. And also you can see the color comparison. So the color of the surface there, and that's stretched a little bit stronger, is very similar to the dark areas on Pluto. Now it's not identical, but it's very similar in color and in spectra to the darkish areas on Pluto. And so that gives us a really nice comparison point. And it shows you how much brightness variation there is on Pluto as well. This area here, Sputnik Planitia, it's nearly 90% albedo. It's really, really bright. These areas are really, really dark. And this object is pretty much over in the dark area. Which makes, most KBOs are like that, which makes them harder to see. So, that was the sort of stuff we got down initially. And then after, we got home, we started to get some downlinks. And so the first thing that we really got after we came out of solar conjunction was this sequence of images. And here you can actually kind of start to see the shape fairly well. So, these are sort of scaled such that they're the same physical size. So it gets blurrier to sharper, just as the spacecraft gets closer. But you can see that we're approaching kind of full on. The subsolar point is kind of over here-ish. So the shadows are going this way, up from they're sort of that way. And that's why we can see a whole lot of shadows on the surface. And why it's pretty much the same brightness. And you see just the angular size how it grows, and that kind of reinforces this is a very fast flyby. So